Hello everybody and welcome to our new video training package of Abaqus. 3D printing simulation in Abaqus, a comprehensive and example-oriented package for advanced Abaqus and finite element users. If you want to start analyzing your projects in Abaqus, it is better to save your time by watching this demo and making your decision easier. Don't waste your time watching amateur and weak videos on YouTube. This package contains 2 lessons and 5 workshops in more than 120 minutes. And here I will present you the syllabus of some lessons and we can see some selected parts of them. In this package, 2 main methods for simulation of 3D printing are discussed. The first method uses scripting and subroutines to model additive manufacturing steps. In the second method, the ADM plugin is used to simulation of additive manufacturing. This plugin is an advanced tool to simulate 3D printing process and cover different ADM processes. In the first and second workshops, 3D printing simulation of shaft and gear with DISP, USDFLD and Python scripting are presented. See some short parts of this tutorial. In the first lesson, you will learn what is additive manufacturing fundamentally and how to simulate it in Abaqus. Some basic concepts are presented in Lesson 1. Take a quick look at the content of the first lesson. Hello dear Abaqus users, I hope you're well. In this training, we are going to teach you the simulation of the additive manufacturing process with the AM Modeler plugin. In general, additive manufacturing or AM is a name that refers to the construction of 3-dimensional objects by adding layers of materials. A 3D computer model is given as input to a device called a 3D printer. That device provides a physical part as output by selectively placing and layering materials. There are several additive manufacturing production techniques, and each varies due to the materials, layering, and machine technology needed. For the first case, powder bed technique. This method uses either a laser or electron beam to melt and fuse the material powder to develop products. The material used is plastic and metal in powder form. This technique itself is divided into 4 types: selective laser sintering or SLS, electron beam melting EBM, direct metal laser sintering or DMLS, selective laser melting SLM. Material extrusion additive manufacturing technique. A filament or thermoplastic material is used to create parts in material extrusion. The filament or the thermoplastic is heated and then continuously layered through a nozzle to make the final product or part. A number of additive manufacturing capabilities are. In fact, there is no concern about the complexity of the parts and the problems of production in the traditional way. See this model? It is a simple gear and the final result should be like this after we are done with the simulation. You see how the layers are piling up and forming the gear. This contour plot animation shows the temperature changes with a scale factor of 20. To do this simulation, we are going to use Python scripting and subroutine. First, you need to know that this simulation will be done in 6 steps. Only 1 layer will be created in each step and its boundary condition will change. In the first step, the first layer is created. The top surface of this layer will be constrained in the U2 direction. Because if you remember from the previous slide, the surface of the current layer is supposed to be tangent to the bottom of the tank and won't be able to move in the vertical direction, which is U2. So we must apply this condition to be like reality. This condition will be deactivated in the next step because the platform needs to move vertically, so the next layer will be made. Therefore, we need to deactivate the constraint. The bottom of the first layer must be fixed from the initial step to the end of the simulation, because like we said before, it sticks the bottom of the platform. The second layer will be created in step number 2. As you see, the U2 direction is no longer constrained in the first layer. So the second layer must be constrained in the U2 direction for the same reason before and will be deactivated in the next step. As we said before, the bottom of the model is fixed. The first thing is importing data. This data includes all values we need for simulation, like the material properties, number of layers, and so on. Now look at the code. The first 2 lines are the code's default. With this code block here, you can insert your desired values for each parameter. When you run the code, several windows will pop up one by one and you can insert your values. Look at the flowchart. I equals 1. Now, if I is less than n plus 1, step number I plus 1 will be created. Then I equals I plus 1 and the loop is repeated till all steps are created. Now let's see how the USDFLD subroutine operates. Remember, we use this subroutine to calculate the elasticity module of the model during the simulation. Now let's open the subroutine file next to the flowchart to walk you through the subroutine. See these lines? They are the USDFLD subroutine interface, which you can copy from the Abaqus documentation. The Y will be saved in field 1 and EY in state V1. These variables will be saved in state V2 and state V3. And after that, the subroutine ends. As we said that this subroutine will calculate the temperature changes. Let's see how this subroutine operates. There is the interaction property. That's better. Change the field output to nodal temperature and displacement next. See this figure? This is the shaft we want to model. There is a groove above it, so when we layer this model, we would have non-uniform layers. We will explain more later. After we are done with the simulation, the final results will be like this. This contour plot is for temperature changes with a scale factor of 16. The layers are piling up and the temperature of the layers changes during the simulation. As we said earlier, this Python code has only 4 differences compared to the previous one. So we just explained these differences and the rest is the same as before. Now we must assign the section to the layers one by one, so we need another loop. This is the second difference in this code. I equals 1 at first. If I is less than n plus 1, then the section is assigned to layer number I. The loop continues till the section is assigned to all layers. Each layer has the maximum temperature when it's created, but in time it cools down till it reaches the minimum temperature in the end. You can see the temperature changes of each layer during the simulation in this plot. At first, the temperature is maximum, then it cools down to reach the minimum in the end. AM Modeler is a plugin for simulating additive manufacturing processes that has recently been included in new versions of Abaqus software. This plugin receives information related to material placement and heat source movement in the form of a series of tables and simulates the 3D printing process using special internal subroutines. In this section, we start main subject of this tutorial, AM Modeler plugin. AM Modeler is a plugin designed to simulate the additive manufacturing process. It is divided into three main parts: data setup, definition, the path and the physical situation of the material deposition tool, and the movement path of the moving heat source in time. Setup model defines the workpiece and provides a preview of the tool path and heat source. Simulation setup settings related to the three main simulation processes, which include the activation of elements, heating and cooling. You see AM3 interface, which is our only communication way with the plugin. The simulation of additive manufacturing is done by eigenstrain or thermomechanical methods. The eigenstrain concept calculates all sources of inelastic deformations that lead to residual stress or distortion in manufactured components. The first layer is added. The first layer is unconstrained. It contracts when negative eigenstrains are applied. The second layer is added on top of the first layer and bonded to the first layer. The contraction of the second layer is constrained by the bonding of the first layer, causing the part to distort and including residual stresses. In fact, simulation based on eigenstrain is a static stress analysis whose purpose is to predict the residual stresses in part under construction. The thermomechanical simulation method is a thermal stress analysis. First, transient heat transfer analysis is performed, and the resulting temperature field is converted into the structural analysis. In general, the thermomechanical method has three main concepts: progressive material deposition, progressive heating of the deposited material, progressive cooling of the printing part. In this workshop, we plan to teach you sequential thermomechanical analysis of simple cube one-direction LPBF 3D printing using the trajectory-based method by AM Modeler plugin. The build part is a cube with dimensions of 1 mm by 1 mm by 1 mm. and the build table is considered as a cube with dimensions of 1 mm by 1 mm by 0.25 mm. You can see the assembled state of the build part and the build table. The required properties in this analysis are the following: conductivity, density, expansion coefficient, latent heat, elastic and plastic properties, and specific heat. The build part starts from here. And this is the build table. The construction direction is global z-axis. The build part is supposed to be made in 10 layers, so the thickness of each layer will be 0.1 mm. Before we go any further, let's walk you through it, what we are trying to do here. In the first step, we'll define two thermal and structural models required to start the AM Modeler plugin. First, a thermal analysis is performed. Then the results, which are a nodal temperature field, will be applied to the structural model as a predefined field. After that, the structural analysis will be performed. Sequential means the thermal analysis is done first and then structural analysis. From the plugins menu, select the AM Modeler Show Height option so that the AM Modeler option will be added to the model tree. By clicking on AM Model and selecting Create AM Model, a window will be open for us. The type of our analysis is thermal structural. We are simulating a process that is already included in Abaqus simulation conditions and is not custom. The model is a sequential type, first thermal and then structural. Heat transfer and static general steps are automatically detected. The models are selected based on the steps. The Model 1 is for thermal and Model 2 for structural. This window indicates that if you click OK, you cannot change the type of the analysis and the type of process and your models. Expand the AM Model 1 and you see three main sections of AM Modeler: Data Setup, Model Setup, and Simulation Setup. We open the table type from the Data Setup and then enter the parameter table. By default, in this version of AM Modeler, there are different types of table parameters. And as explained in the AM Modeler plain tutorial, a number of them are used for each problem. You see ABQ AM moving heat source, one of the required parameter tables in the simulation. It has two rows. The first row is related to the event series of laser motion, and the second is related to energy distribution, which can be concentrated, uniform, or golden. Enough about the material, let's see the thermal analysis. First, let's talk about temperature changes. At the beginning of the analysis, there is only the build table, which has an initial temperature of 80 degrees Celsius, as we expected. The temperature remains almost intact till the first coat of powder is added. In 0.4 seconds, the first coat of powder is added completely, and it's ready to be scanned. This is a heat transfer analysis, so the temperature is a little bit decreased because of the first layer. After the coat of powder is added, the laser scans the material to form the layer. The temperature and heat flux increase till the scan is finished. For the final thing, let's see the temperature changes of a node in a plot during the analysis. Now it's time to run the structural problem. We have the first layer now, and there is not much change in the stresses. We are in 0.4 seconds. The laser will start scanning the model, and we must expect a considerable stress increase. Finally, it is done. Let's summarize before we say goodbye. So, as a summary of this workshop, we made two thermal and structural models and entered them into the AM Modeler plugin. After applying AM Modeler plugin settings, we performed a thermal solution, applied the resulting temperature distribution to the structural model. Finally, we presented the distribution of stress, strain, and displacement caused by the 3D printing process under the title of Structural Results. In this workshop, we're going to teach you how to do a 3D printing simulation by AM Modeler plugin with FDM and LDED methods. This workshop will present simulation of 3D printing of a wall by the Fusion Deposition Modeling or FDM method using AM Modeler plugin. Now that you've understood what a bead is and how the FDM forms the model, let's see the bead dimensions of our own model. The bead height equals 0.9071 millimeters, so each layer's thickness would also be this value. Therefore, the number of layers will be 12. The bead width equals 3.35 millimeters, and there will be 3 beads in each layer. This is how the model looks when we mesh it according to these data, which will be explained later. As we said before, this simulation is sequential thermomechanical analysis of FDM. This means a thermal analysis must be done first and its results will be applied to the structural analysis. In the AM Modeler plugin, you must select this option for the analysis type and select the Fusion Deposition Modeling option from the process type combo box. We will explain more in the Abaqus. As we said earlier, we need two models, one for the thermal and one for the structural analysis. The differences between these two models are in the step and load modulus. Therefore, we create one model, then make a copy of it and apply the differences. Click on this option from the Plugins menu to activate the AM Modeler plugin. You can see that the AM Modeler tab appears with the Models and Results tab in the Model Tree area. Now select the AM Modeler tab and double-click on this item. First, you can name your AM model. Next, you must select the analysis type, which is thermomechanical. Specify the process type from this combo box, which is Fusion Deposition Modeling. In the following section, the thermal and structural models must be selected, which has been done automatically. Click OK. Now you can see that your AM model has been created, and there are 4 items that you need to attend to. The first item is the event series. Double-click on it. The second item is the material input. Here we must specify the deposition process type and define the progressive element activation. You can change the name of these settings by the name field. In the material deposition section, you must specify how the deposition process must be done. In the Basic tab, you must select a proper event series which was defined in the previous item for the material deposition. Next, the method of the deposition process must be selected. Roller or bead, which is the bead in this analysis. In the energy distribution combo box, you must select the desired method for the distribution of the heat source energy. Set to concentrated to indicate a point energy source. To uniform to indicate that energy is distributed inside a box shaped of finite size. Or to goldak to indicate that energy is distributed over a 3-dimensional space following an exponential expression. The next item is cooling. We have both convection and a radiation heat transfer in this analysis. The settings are the same as in the previous workshop, LPBF. Therefore, we just enter the values. Let's see the complete results. First, let's see the printing. Select the Part Instances option from the Color Code combo box for better displaying. Now use the Animate tool to see the printing. You see each layer is being printed by depositing 3 beads. Also pay attention to the deposition direction of each layer. Odd-numbered layers are deposited in the positive direction of the x-axis and even-numbered layers in the negative direction of the x-axis. At first, the temperature of the substrate is 80 degrees Celsius. The temperature rises when time passes and the first bead is deposited. This is the location of the nozzle's start point, just as in the event series. The oval shape represents the Goldak distribution. The first layer's bead is deposited at 9.58 seconds according to the event series. And this is the end point of this bead. Printing the other layers would have the same procedure. Each bead will be printed, the cooling process, and the next bead will be printed. In this workshop, we're going to talk about some special purpose techniques and user subroutines that are available for machining and material removal processes, which often follow an additive manufacturing process. This workshop will teach you how to do a material removal process on a simple cube like this one. There are several types of material removal process due to the bead variables, which are bead dimensions and orientations. The simple one, variable bead size, arbitrary fixed bead orientation, and rotation bead. Each of them has its own settings and the ABQs, as you see here. There is a cube in all simulations and you can see its dimensions in this figure. The material properties are conductivity, density, and specific heat, and there is an initial temperature. All units are in the SI millimeter system. Now see the material removal frame by frame from the beginning. You see how it's done. This is the simple type. Now see the material removal frame by frame from the beginning. Now see the material removal frame by frame from the beginning. As you see, the bead is rotated, and according to what we said in the slides and explanations about the advanced options, the hole is shaped like this. As you see, the bead rotates throughout time, making the hole look like this. You can accommodate the event series data with these results and figure out why the hole looks like this. Our support is one of the main advantages of 3D printing simulation in Abaqus package compared to other Abaqus tutorials on the web. I hope you have got enough information about this package, but don't worry at all. If you have any questions about this tutorial, ask us via support@caeassistant.com.